there is equilibrium point. If you have a short circuit in the system, the equilibrium point will start, the system will start moving away from the equilibrium point and until you clear the fault. And if you have, this is an extreme case, academic case, if you have a harmonic oscillator, no damping whatsoever, this will be trapped for error and you will have oscillation until you do something. So what is the idea? We connect here that this oscillation, the center of the oscillation can be connected to the change in the equilibrium point. So by changing the power in a stepwise fashion in this component, we can change the center of the oscillation and we can change the orbit to the one that you can see in red. So the question here is at what time I'm going to change this center of the oscillation to provide full control. And the idea is explained here graphically. So if I change the equilibrium point to this new equilibrium point, I need to put my glasses. So the equilibrium point is XC. Then when the system is oscillating, at this point I can give an order to step change the power in this component, and the system immediately will change to a new orbit. And as soon as in this new orbit the equilibrium point passes to the original equilibrium point, I can restore the power in this component and the oscillation will be eliminated from the system. So that's the principle, the idea, and we have a system that is modeled in a linear way, and we have proved that this concept actually works, and we tested in this three-machine system, and as you can see here, we have initial switching when you have the step change in the power, and another switching when you restore the power to the initial power of the components, and the amplitude of the oscillation is reduced significantly. But that's a very simplified model. So we tested also, the same concept, we developed the algorithm and the mathematical function we need to take the decision when we're going to have this step change in the power, and we apply it to a larger system. We have a 10-machine system here with full nonlinear model for power flow equation and machines. The machines also are nonlinear with AVRs, governors, and all the models that we typically consider. And we apply a short circuit here, this pass, and of course, this is still at the academic level. We are trying to replicate a case where the oscillations are sustained. So the oscillation, as you can see after the fault, you can see clearly in the angle here, the system is oscillating, and we're assuming here there is no other control than this new mechanism that we're proposing. So if we apply this logic that I presented to you this morning, then this is a proof of concept that the oscillation can be significantly diminished. So in this case, the first switching happened at 1.8 seconds, in which we step change the power in this component, and then at 2.3 seconds, we restore the power to the initial operating point, and the oscillation in the system are significantly diminished. So in this case, I am presenting here the projection of the system trajectory in the different subspace of the system. And this is the significant oscillation that we have. This is the mode related to that. And this is the case without control, but when we apply this discrete control, you can see in this plot that the oscillation is fully handled, and we can reduce the amplitude of this oscillation significantly.